Hello. Good morning. Welcome to NetDevConf. Thanks for coming. And my name is Adrián Moreno, and together with my colleagues, Paolo Valerio and Antoine, it's not this Antoine. There's another Antoine. Yeah. Antoine Tenart, yeah, that one. Yeah. Yeah, that's better. Thank you. Together with my colleagues, Paolo Valerio and Antoine Tenart, we're going to be talking about debugging virtualized networks with Retis and the challenges that we found. So, well, we have written a network troubleshooting tool. It's called Retis. What we want to share with the NetDev community today is the challenges that we've found and how we've tried to solve them, and maybe showcase the tool along the way. So in a nutshell, just jumping right at it, these are the challenges that we found. As any network inspection tool, we found three big challenges, which are the fact that there is not a coherent source of data, the fact that there are lots of packets traversing the kernel at a given time, and the fact that these packets mutate over time. These are the big challenges. For us, we had an additional requirement, which was to have this solution working in Open vSwitch, which brings another challenge, as we will see. So these are the challenges, and this is the agenda for today. We're going to go deeper into each of these challenges, explain how we try to solve them, and maybe show some examples of Retis along the way. Actually, let's start with showing an example. Let's imagine that there is an ICMP flow or traffic flowing in our system, and we want to know more about it. Maybe we want to troubleshoot it. Maybe there's something going wrong. We could run Retis with these arguments, which, as we will see later on, installs some probes in these well-known trace points in the kernel, in the Netdev layer. And Retis will print the event, the place where it happened, where the packet was seen, and the information, the header information. So it is very similar to what TCP dump would show. We see it is at least going through a couple of network devices. During the presentation, we will be enriching this example with more arguments, with the end goal of trying to better understand what is going on with this ICMP traffic. And now I'll leave it to Antoine to start digging into the challenges.
Yep. So the first challenge is about the amount of data available and about where the data can be retrieved, because the networking stack is quite large. So collecting data from all over the networking stack is very different from making a kernel modification in a known place, because you need to take into account a few more things. How to actually get the data, because getting data from argument in different eBPF prop types is not the same. There can be indirection to get the data as well. But also, and more importantly, how to parse the data. It is in an unknown state, because you can probe in any function, you cannot make assumptions. So data might be uninitialized. You could have pointers not pointing to the right location, and many things of the like. So this needs to be taken into account as well. Plus also some prop-specific limitation, limiting what can be implemented. Not everything is available in every prop type in eBPF. So the first challenge is really a need for a uniformization layer when you write such a tool. You also need to select the right eBPF feature set For example, which kind of prop types do you want to support? Because this will have an impact about what you're about to do. So a few things you need to do is to uniformize the input to get the right argument, to get indirection. But also, for some examples, you need to uniformize the eBPF API if something is not available in a given prop type. But also some quirks. There are many, but one example would be red probes don't have access to input arguments. So if you do want to have access to those input arguments, you need to do some, to put things in place, to have some tricks to be able to do so. But also in addition to this, Retis can also run in a variety of environments, meaning different architectures, different kernel versions, kernel configurations, and not everything might be available or working the same way. Like one extra example would be a function might be inline. So if you rely on that function to be available, you will need to have some things in place for the tool to be to run in that environment as well. And now up to Paolo.
Yeah, thank you. In the next sections, we are going to introduce how the tool looks for data and the means it offers to limit the output. Packets usually traverse different components, and in Retis, we opted for a modular approach with information retrieval split among collectors. Each collector takes care of specific information, with CT, for example, in charge of extracting data from the NFCT member of the skbuf, or the NFT collector in charge of tracing the packet going through the NFT rules. And some more collectors whose output will be shown in the next slides. Some collectors, when enabled, request to load and attach programs to specific functions or trace point to fulfill their tasks, like NFT, skb drop, and also skb tracking and OVS. The remaining ones simply extend all the programs. We mentioned collectors extending main programs, and to do so, programs include a series of calls to global stubs. Stubs are then replaced at load time by a proper function implementing the actual logic in a way that the result is extended only by the intended code. The initial motivation of the f-replace approach was a combination of reasons. First, it fitted well the modular idea we had in mind. It then theoretically simplifies potential ordering and precedence, if ever needed, and also the one that probably was the strongest reason when we started, which was allowing users to provide their own custom hooks. But custom hooks are no longer a goal at the moment, and so we are considering also using f-entry, f-exit types. So we are trying to simplify here, compiling all the code, enabling the relevant part through read-only data as needed. And back to our example, here a few collectors are added, in this case NFT and CT on top of the skb we've seen. We are probing another function skb scrub packet. And we also enable another skb section to dump the network namespace in addition to the device section. It is also worth noting the option allow system changes. This is required for the NFT collector as it adds an NFT rule enabling tracing. And running the command, Retis now shows the events and how the namespace information gets updated. When we hit the XBit trace point, the enum related to the namespace is the one from where the ping originated, whereas in the next events, we have visibility of how the information changes. Besides, the output also shows us the packet going through a bunch of NF tables rules, with tables, chain names, verdicts, whether this is a policy verdict, and handles, and the CT data associated with it, reporting the state, the status bits, the 5 tuple in both directions, and so forth. Here we've shown the relevant events, but obviously if you run these commands on your system, you'll get a lot of noise as you capture every packet multiple times, depending on the number of probe points. And noise introduces the next section, which is about filtering. Capturing and so processing many packets has different aspects to consider. In our case, for example, it may lead to ring buffer exhaustion, like in the case user space is not fast enough at dequeuing events. Also, if we consider storing the capture in a file, the number of events has a direct impact on its size and a potential impact on the post-processing time as well. In general, narrowing down is just more convenient. We then implemented two ways of filtering during the capture process. One way that is essentially packet-based, and so matches happens against the packet header, and the other that's based on skbuff fields. The idea of packet filtering was mostly inspired by BPF convert filter in the kernel, and what we do is compile a pickup filter expression into CBPF, simply using libpcap. The CBPF instructions are then converted into eBPF with loads in the packet data happening through helpers calls. But there are some limitations though, one of which is that no BPF extension support is present, and this could theoretically be a problem, for example, in the case of VLAN matches, depending on where the programs are attached. Given the resulting eBPF filter, then our first iteration approached the filter insertion, extending our programs by replacing a stub, just like we do with hooks. But we then hit a problem. We had to deal with an older kernel and pointer arguments to non-context data and global functions. We considered potential workarounds, but we were also considering DF entry adoption as an alternative to kprobes. And again, we were on the path of simplifying, as extending those type could be problematic. We eventually opted to dynamically inline the filter registering program handlers. Basically, program have an invalid placeholder call, and that instruction is used to determine where the filter has to be written during load. The second way of filtering is through metadata. In short, numeric and string matches can be performed against fields belonging to skbuff or inner data structures. The slide shows a list of examples matching against the skb mark, a match against a bit field type, and a slightly more articular match against the com mark, and lastly, the device name string comparison. Some limitation exists, but the main one for this type of filter is that at the moment you cannot match multiple fields in a single expression. And this is a quick overview of how the previous example of the NF com-mark match work. Things are slightly different for bit fields or string, but most of the operations apply. User space gets the BTF info for struct skbuff, determines the offset of the NFCT member, creates an entry in a map that represents a load pointer operation. It then gets the BTF info of an fcon and proceeds calculating the offset of mark, creating another entry in the map with the required information for loading it. An additional entry for the right-hand side literal is created. On the eBPF side, the entries are read, and every time a load PTR entry is found, probe-read kernel helper gets called, updating the base address with the pointer read. The values, of course, get masked. And for non-PTR load, another call to probe-read is done, and the comparison against the RHS is performed, returning the verdict. And back to the example, as we've seen, the syntax for packet filtering is simply the one defined by pickup filter. And here we only match ICMP packets with the specific source IP. For simplicity, we did not include a metadata filter here, but when both filter types are present, events are generated only when both match. And yeah, the output only includes the intended matching packets. However, we might still have a problem. Operation like NAT can happen throughout the packet path. Filtering then is not enough if we want to still receive events related to packet going through manipulations. And so we need the help of an additional component, which we are going to see in the next slide. And what's next for filtering? On the packet filter side, the plan is to introduce the support of meaningful BPF extensions. We mentioned PLAN. And on metadata filter side, we have a series under review, introducing Boolean expressions, lifting the current limitation of a single match. Also, metafilter doesn't strictly depend on skbuff, so the long-term plan is that we want to extend this to non-skbuff types like generic arguments or return values. And now back to Antoine that will introduce the next section.
So another challenge we just saw is about the packet life, especially as one packet can be modified over time. And also remember, we're saying the same packet multiple times because we are probing to different functions in the networking stack. So different kinds of mutation can happen for a packet. We saw one example where the packet can be modified. That would be NAT, but also encapsulation and other kinds of transformations. But in addition to that, the Linux networking stack specifics can have an impact, such as clones or relocation, modifying what's around the packet itself. Also, another unrelated aspect linked to tracking packets in Retis is that we will be reporting the same packet multiple times as it probes different places of the stack in parallel. And because the system is very likely to see multiple flows at once, events will be interleaved, and that is very hard to follow in the output. So there's a clear need to track packets, but what's a packet? And that's probably the right audience to ask this question. So in short, there's metadata and there's data. So here we're mainly speaking about struct eBPF and the head pointer. There are also other objects that could qualify. I'm thinking about XDP or early TX, but that is out of scope in this presentation for now. So what to track then? Both tracking the metadata and the data works, but there are some things to consider. One is memory can be reused. So if you track a memory address, you need to take this into account. And also the networking stack can have, specific can have an impact, such as clones, or even the head can be relocated. So what to actually do? There's no clear solution, all require some tricks. In Retis, we chose to track the data itself because we felt like it has more advantages and based on our experience. But your mileage may vary on this. So in practice, we report two fields. One is linked to the data part, and that's what we call our main tracking ID. This is what we use to track packets. So as long as two packets have the same tracking ID, for us, this is the same packet. But we also report one which is linked to the metadata itself, because that will help to distinguish between clones, for example. So we have an example which is highlighted, and here we can see the unique identifier contains the head pointer and the timestamp of the first time we saw a packet, and that helps with memory being reused. But also we do report the SKB pointer to be able to see clones, for example, when a packet is taking two different paths. So you can see on the slide what the whole reporting data can look like. We have an ID, the main ID to track packets, and then the SKB address. And also on the link provided, you can have a look at most of the tracking logic we have, and especially where we do add specific probes to be able to track a packet. What's next? So things mostly work, but they could be way simpler and more robust. We are also not the only project looking at solving this. So one solution would be to have the ability to associate a tracking ID directly to a packet. That would be best because we wouldn't have to do it ourselves. That should be doable from eBPF probes. We are using K probes, trust points, but also we might use FN3 and many other kinds of probes. And that tracking ID might be able to survive clones and other modifications, but that's probably up to discussion because you might or might not want to have these things working this way. There's another talk at Netdev this year about rich packet metadata. Also, an RFC was posted last week, and it seems like this might help, but might need to be improved a bit for our use case. We will need to have a clear look at that series and probably discuss it in Netdev with the authors to be sure that could be a solution. If that turns out to be a solution, there could be a room for collaboration between debugging and visibility utilities, because remember, we are not the only one trying at solving this. And there are also other questions like, should setting a tracking ID be part of the kernel, or should the kernel be aware of a tracking ID? One thing that could happen would be reporting that tracking ID in various debugging things in the kernel, and that could help to correlate event between different tools and what the kernel is reporting. So there are room for discussion on that. Back to the example. So to get tracking, we enable the SKB tracking collector, as you can see in the example. We are also adding the -O option to store events on disk for later post-processing. And during this collection, we are now seeing the tracking ID in the event as we just saw. So you can see there's one event displayed on that slide. It's a bit modified, but you can see there's a tracking ID associated with it. So you can have a look at all the event and see the tracking ID to have an idea about if two packets are related. But there's a simpler way. Once the collection is done, we can sort the event using the Retis sort subcommand. And this subcommand will use the tracking information to group packets and reconstruct their journey. Group packets are also sorted by timestamp. So here, the first packet of a group, which is the first packet that was seen for a given flow, is printed. And then the other packets with the same tracking ID are printed too. Slightly indented. We can also see the packet number in its own flow. So we see N0, N1, 2, etc. In this output, we can see there's a gap. So we have two flows, but it's probably the same packet. So even though we had tracking enabled, all the packets were not grouped. But we'll come back at this later. Also, if we scroll down a bit in the previous output, we can see the packet is being source netted. And thanks to the tracking virt feature, we're still reporting and following those packets. So even though it's not matching the filter, we are still seeing those packets in the tool. Also, we enable the NFT collector while making the collection, and that is giving us extra information about the table, chain, handle, and action followed by netfilter. So this can, for example, be used to find the right line in the netfilter configuration. And now back to Adrián.
Okay. So remember the gap in the previous, the gap there. Essentially, Retis thought there were two packets, but we only sent one of them. So let's dig into what happened there. First, we need to understand how OVS works. This image from an early paper shows it very clearly. The data path, the kernel data path is essentially used as a cache. The first packet that hits the kernel data path is sent to user space. In user space, OVS figures out what to do with it. It gets re-injected back to the kernel, and the flow gets installed so that subsequent packets are processed by the kernel directly. So if we zoom into this image a bit, what we see is that When a packet comes to the kernel data path, OVS kernel module, it hits a trace point called OVS DP upcall. Then the packet might get segmented if it's GSO, and multiple calls to queue user space packet happen, which eventually enqueue all the packets, all the segments into netlink sockets. In user space, there is handler thread pool, which process each of these upcalls. And eventually, there are two commands that are sent back to the kernel. There's a command called flow execute, which is essentially the packet reinjection command. It injects the packet alongside some actions to be executed on it. And then the flow put action command, which installs the flow so that subsequent packets hit the flow in the kernel and are processed directly. These commands are enqueued back into netlink sockets. And we have a couple of, a function, a kprobe that gets called once per packet, and then multiple trace points are called per packet on each action that gets executed on them. Thankfully, there are USDT probes in user space, and like user statically defined trace points in the user space part, and normal kernel kprobes and trace points available to get the data needed. So now we face the challenge: how to track this packet. So we get the information, but how we know it's the same packet as we saw in the kernel? So we need some kind of identifier. We considered using the netlink sequence number, but then on second thought, that was not, it didn't feel like a good idea. The socket where the packet gets reinjected might not be the same one as the one that we used for the upcall, and all sorts of other quirks that we would have to, it would be essentially abusing the field. We could use an OVS-specific upcall ID, something like that. We were tempted to start working on that, but then this rich packet metadata idea came up, which we already mentioned. And this packet metadata in OVS, we should persist it across upcalls anyway, if we don't want to break all of the tracking utilities that rely on it. So we might as well use it. There are still open questions, such as how are we going to reinject the traits? Are we going to use a blob, or are we going to understand the keys and values and stuff like that? But at least it looks like a promising way forward. What we end up doing? Well, we generated an ID based on a hash of the data of the first bytes of the packet, and some knowledge of how OVS works internally to correlate the USDT probes and stuff like that. This identifier is not the same one as we generate for SKB, for escape buffs. So we need a post-processing tool, which we already have, which is called Retis sort. We already showed before. And Retis sort will basically stitch all the tracking identifiers together. But this is not the only challenge. Using USDT probes is a challenge in itself. Essentially, there is no BTF, or not readily available. So there's no Cori. So there is a problem with essentially we have very little flexibility to introspect data structures. So if the data is not available in native types in the USDT probe, then we cannot consume it without going down a compatibility nightmare. So we had an idea that we have explored, and we want to explore a bit more, which is getting the debug information from the dwarf information from the debug package, transform it with tools such as Payhole into BTF, and then do Cori. libpf supports doing query with whatever valid BTF we can build up. So in theory, it could work. We have done some experiments, and they look kind of promising, but there's still a lot of work here. Of course, we don't want to rely on pay-hole binary existing in the system, so we could build something up inside Retis. Yeah, still a lot of things to think about. If we go back to our example and we add OVS and OVS track, the result is now we have a coherent, sorted list of events associated with our packet. I've modified a little bit the output so it fits nicely in a slide, but essentially we see how the packet is sent through a net device. It goes through a network namespace. It gets upcalled. It is then there are the operations applied on it. It is then re-injected back into the kernel. OVS executes an action on it, which happens to be output to port number 2, which is another net device, and the process of this packet continues through NF tables. We see how the packet gets natted. We see the exact table that configured that NAT. We see the contract state associated with the packet at the time, and we see how the packet gets transformed and ends up in the destination network device. So with this, we can wrap up the presentation. We have some extra features in Retis, which we don't have time to show today. We have Python bindings to basically allow users to implement any kind of post-processing, of custom post-processing utility. We have easy to share YAML files in order to share these potentially long command line arguments. And we have some really cool stack analysis and automatic probe installation, and many more features. So, of course, we invite everyone that is interested to play around with the tool. And just to recap, these are the open questions and the areas of future work. We want to make sure the availability of the API that we're using, the libpcap API that we're using to replace the filter is kind of guaranteed, because we are relying on it. We need to work with the SKB traits. We need to look into it and make sure it works for us, or try to make it work for us, and try to make it work for OVS subcalls. There's also room for future for collaboration in making some shared packet tracking infrastructure, whether it's in eBPF or in the kernel. And there's the open question of how to do query for user space applications. And with that, I think we can close the presentation. Thank you very much for listening. There are a couple of links here if you want to try the tool. And we have a couple of minutes for questions, if anyone has any. Yeah, microphone is coming.
Hi, Jacob here, the other Jacob. I'm working on rich packet metadata with our guys from Cloudflare. So tracing is definitely, and tracking, definitely one of the use cases that's driving the work, which we'd like to support, including tracing flows that get intercepted into user space and then re-injected. I already saw your tool when you presented back at DevConf, and I was actually planning to extend Retis it's kind of a proof of concept demo for rich packet metadata to make sure we have everything we need in the kernel to support such use cases. So if you guys want to help me do that, that would be great. If we can work on it at this early stage. That said, I have one other question. Why is it named Retis? Where does the name come from? Because it doesn't ring any bells for me.
Well, we definitely would love to work with you guys and get Retis supporting the SKP traits for sure. So yeah, let's talk afterwards. The word Retis, we came up with, we did some brainstorming with words. Retis, I think it comes from the Latin root for network, and yeah, we did a poll with some friends and colleagues, and it won. So we respected the democratic output, and we named it Retis. By the time Retis was a very hot topic, so maybe it was not very fortunate, but still.
Hello, I'm Eugene Crosser. Could you say a couple of words about rich packet metadata? Where, like, what is it, where does it live, and how exactly you are, not exactly, but in general, how you are making sure it's preserved over this upcalls, rejections.
Yeah.
Thanks.
That is actually the work that we have to do right now. So rich packet metadata, it's currently an RFC in the list sent by our friends in Cloudflare. It is very promising because there's a presentation on it. I think it's tomorrow, but it essentially uses the headroom to store some arbitrary metadata, and that's precisely the challenge. How can we preserve it across, especially in OVS is especially challenging because the packet gets, the SK buff gets consumed in the upcall, and then a new one gets created from thin air on packet reinjection. So we kind of need to preserve that metadata across, or else we would be breaking any tracking application that relies on it. So to answer your question, it's work in progress, but a promising way forward for Retis and for OVS tracking. Yeah.
Thanks. For the specific OVS use case, I think you might want to look into what you would do for proxies as well.
Sorry, say that again?
What you would do for proxies. So a proxy hijacks the connection and injects multiple packets, maybe even because it picks a different MTU. How do you track that and say all these packets are associated to my initial packet?
Exactly, yeah. OVS is not the only application that can hijack the traffic and reinject it. There's even NFQ that and there's a native net filter API to do exactly that. So yeah, we need to figure out how to do it. Okay, in that case, thank you very much.
Thank you.
Thank you.